All right, so, thank you. All right, this is where we left off. Yeah, looking at dipole-induced dipole interactions. So we had our water, which has a dipole, and it induces a dipole on the oxygen molecule here, which previously did not have one, okay? So slightly stronger interactions than van der Waals interactions, but definitely not the strongest that we can get. So moving on from there, we look at dipole-dipole interactions. So in this case, you have a molecule with a dipole that is interacting with another molecule that has a dipole, okay? And this tends to be the strongest type of intermolecular interaction. So if we have water, okay, and we have this polar OH bond, so water has a dipole associated with it, okay? And we have another water. What we find is that the partial negative oxygen will interact with the partial positive hydrogen, forming an attraction. And it's a fairly strong attraction in this case. Okay? All right, now as we'll see, these dipole-dipole interactions are actually quite significant, especially in terms of water, and in determining the properties of the bulk material. Okay? So the interactions between the molecules, all right, have a definite effect on what we can observe in terms of the bulk. So water sitting in a beaker, for example, which I have one over there, but that's for something different. So if we look at a series of related molecules that interact via dipole-dipole interactions, and if we start by looking at methane, okay, so we have fairly electronegative carbon with 4 hydrogens around it, and as we move along move down the group and along the series, so you'll notice if you look at the periodic table, okay, you have carbon, silicon, germanium, and tin. So we're changing that electronegative element in the middle. What you see is that I believe it's boiling points. Yep. The boiling points will increase in temperature as we move along. And this trend holds fairly steady for the majority of molecules that interact via dipole-dipole. However, if we look at this one here, which is just one more group along the periodic table, you'll notice that water has a really, really high boiling point compared to its counterparts in the series dihydrogen sulfide, dihydrogen selenide, and dihydrogen telluride. Okay? So water is a fairly special case, and quite obviously these dipole-dipole interactions are fairly significant for water and a lot stronger compared to what we would expect otherwise. And so these unusually strong interactions of water are what are termed hydrogen bonding. So as we'll see, hydrogen bonding is actually really, really important, especially in terms of how water acts and its properties, especially within the environment. So, are we ready to move forward? No? Okay, I'll give you a few more seconds. Alright, so basically, alright, these hydrogen bonds are fairly strong intermolecular forces, and in solid water, ice, it actually orders the structure it packs together. So if you think about solid, the molecules are very, very close together, yeah? And so if we have these intermolecular interactions that we have to account for when water packs together to form ice, it forms in such a way that we have these hydrogen bonds forming, and what we get is what's a fairly open structure compared to, say, liquid water. Okay? Now, this affects the properties of water, and it makes ice less dense, so hence why we have icebergs that float. Okay? Now, this is a good thing for fish because it means that ice on a lake is at the top of the lake and the fish can still survive during winter underneath it. Okay? It would be a bit annoying if the water froze from the bottom up. Okay? So it makes ice less dense, It also means that ice takes up more volume than liquid water. Okay? So as it packs, it's forming this rather open, structured lattice, and that takes up more volume. And this is why, especially where I grew up in Central Otago, for those of you who don't know, and it gets very, very cold in winter. So if you went away during winter, you would actually have to drain all your pipes so that they didn't freeze and they didn't burst. It got so bad one year we actually had to put ping pong balls in the toilets so that they didn't crack when the water froze. Okay? So this is an intrinsic property of water that's really good in the environment because it's used for weathering rocks. Okay? So top of a mountain, the water freezes, it gets in the cracks in the rocks, it freezes, it expands in volume, that actually cracks the rocks and allows them to weather and move through the geological cycle. So there's a few things there. There is also, I believe, if this goes, these go, maybe not, all right. I know it's here somewhere, so we'll find it. There is a video. Dropbox. That one. It's called Ice Bomb. Right. Who's familiar with Max and who knows how to get it into full screen? The two. That one? Yeah. Awesome. All right. Can you guys see that? Sort of? Yeah. All right.
The ice bomb illustrates the fact that the volume of ice is greater than the volume of an equal mass of liquid water. Some cold water is poured into a cast iron bomb, and a threaded plug is screwed into the bomb so that the bomb is tightly sealed. The bomb is then placed into a dry ice acetone slush, which is at negative 77 degrees Celsius, and will cause the water inside the bomb to freeze. A wooden box is placed over the top of the bomb and slush back. It takes a short time for the water to freeze. When it does, the bomb explodes. Some of the dry ice acetone slush is blown onto the explosion shield. Little bits of the cast iron bomb are left. When the water freezes, tremendous pressure is produced. The pressure is enough to cause this cast iron bomb with more than 1/8 inch thick sides to burst.
Okay? So it's actually quite impressive what water can do when it freezes. Ah, awesome. Cool. All right. Not used to Max. Sorry. Okay. So you can see what happens there when water freezes and the volume suddenly increases. So if you get rapid freezing like that, you can actually cause things to explode, which is quite cool. Right. So that brings us to changes of state. Okay. So when a compound changes its state, and remember I said the three important states that we're looking at were solids, liquids, and gases. And what that means is that the intermolecular forces which are holding the molecules together in a particular state need to be overcome or strengthened to move it from one state to another. So if we're going up the scale from solid to liquid to gas, then we have to put more energy in to overcome the intermolecular forces and move into the less stable, held together state. Okay? So when you understand the nature of intermolecular forces in different compounds, we can understand why they change states at certain temperatures and why they change states the way they do. So we're going to look at a couple. So when we melt a solid, we have to add enough heat to break all the molecular forces that are holding those molecules together as a tightly packed solid. Okay? So theoretically, if I added enough heat to the disk, it should melt. However, that's not going to happen in an oxygen-rich environment. That's just going to cause it to burn. But you get the idea, right? If you put enough energy into the disk, then you should be able to break the intermolecular forces. It should turn into a liquid. Yeah? So the stronger the intermolecular forces, the more heat you have to add to melt that solid. So as you see with water, the molecules are very ordered and the attractive interactions are maximized. So that means you actually have to put in quite a bit of energy to get it to melt. Right? Hence why when you think back on that diagram that we looked at before, okay, the boiling point of water was way up here, everything else is way down here. The interactions in water are maximized so much that the melting point and the boiling point are that much higher than the related compounds. So if we look here, for example, at the melting points of methane, which is just van der Waals interactions, okay, the melting point is minus 182.5. If you look at water, which is dipole-dipole interactions, then we've got a melting point at 0, which we all should be familiar with. Sodium chloride has full electrostatic ionic interactions. So you've got a full cation and a full anion rather than just two partial charges. So we have an ionic interaction in that case, and what you'll notice there is a very, very strong interaction, and the melting point shoots up to 801 degrees Celsius. All right, so the same sort of thing when we boil a compound, okay? So we're then turning from a liquid to a gas. So you've got to put in even more heat to break those intermolecular forces and then move into the gas phase. Now in the gas phase, right, at that point the molecules are that far apart that we consider them to have almost no interactions at all. There are some, but they are very, very, very weak. And the way they behave, you would think that they have no interactions at all. Okay, so gas will fill up a container of any volume. All right, it can't be poured, it's just everywhere. All those sorts of properties. And again, that depends on how much energy that we put in and the nature of the intermolecular forces. So if we look at the same three compounds, but this time we're looking at the boiling points. Okay, the boiling point of methane is only about 20 degrees higher than its melting point. Okay, so again, that's weak van der Waals interactions. Water, as we all know, boiling point at atmospheric pressure is 100 degrees Celsius. All right, that's our dipole-dipole interactions. Here's a really fun one. Okay, sodium chloride, which is again those pure electrostatic interactions where we have ionic bonds formed. Okay, the boiling point shot all the way up to 1,465 degrees. Okay. I have been a student, and students do sometimes set the stove on fire. Good way of setting the stove on fire is to dump a whole heap of salt on it, I have found. Okay, that's because it doesn't burn that well and it doesn't melt into about 1,500 degrees Celsius. Okay, I doubt any kitchen fire is going to get that hot. I'm not a very good cook either, by the way. All right, so at any point in time when we have a liquid, okay, what's happening is you have an equilibrium with the gas phase. Okay, so if you have liquid water at a particular temperature, the molecules in the water, some of the molecules in the water can gain enough energy to actually break the intermolecular bonds in the liquid water and move into the gas phase. And this is what we call vapor pressure. Okay, so the vapor pressure of a liquid is its propensity for some of its molecules to gain energy and break intermolecular bonds and move into the gas phase. And what you find is that vapor pressure, okay, will increase as you increase in temperature. So as you increase the temperature, you give more and more energy to the molecules in the liquid phase, and so they can break the intermolecular interactions in the liquid phase and move more into the gas phase. So you're basically giving them enough energy to break their molecular bonds and escape. Yes, so at any temperature there's going to be an equilibrium between two phases, but as you decrease the temperature, you're going to change the equilibrium constant. Okay, so at lower temperatures you would end up with more molecules in the liquid phase and very few in the gas phase. As you increase the temperature, then the equilibrium shifts from the liquid to the gas, so you get more and more escaping to the gas phase. All right, so what happens, okay, as you put more heat into the liquid, okay, and the vapor pressure increases, it gets to a point where it becomes the same as the atmospheric pressure. Now, at that point, we say the liquid is boiling, because at that point you've added enough energy that you have increased vapor pressure enough that it's basically the same phase, okay? So you're moving right through, okay? Now, that means that boiling is dependent upon atmospheric pressure and what atmospheric pressure is. So if you're somewhere where the atmospheric pressure is lower, then the boiling point of, say, water is lower as well. Hence the example here, okay? It's harder to boil an egg on top of Mount Everest because the atmospheric pressure is lower and the water boils at a lower temperature, okay? So if the water is boiling at a lower temperature, the phase change is occurring at a lower temperature, so the liquid will never move above that temperature. So in that case, I think at the top of Mount Everest, it's about 80 degrees Celsius. Okay, it's going to take a bit longer to boil an egg. Okay, so basically what you can see is that changes of state are very dependent upon temperature and on pressure. And so those ancient chemists that were around 200 odd years ago were nice enough to measure properties and things at a range of temperatures and pressures, and they put together these things. This is a phase diagram, and it basically gives you an idea of the changes of state that occur at different pressures and temperatures for a particular material. So this is for water, okay? So atmospheric pressure, 1 atmosphere, okay? As you move along 1 atmosphere, you notice that we change from the solid to liquid at the melting point, 0 degrees Celsius. If you keep moving along and increasing the temperature further, once you hit 100 degrees Celsius, you move across this phase line and into the vapor phase. If you decrease the pressure, you'll notice that these changes occur at different temperatures, until you get to a point which is here. Now this one here is what we call the triple point. This is where all 3 states exist at some state of equilibrium, okay? So you can have all 3 states existing at this point. And for water, this is 0.006 atmospheres, so it's very, very low pressure, and 0.01 degrees Celsius, so it's fairly cold, okay? Below this triple point, as you increase the temperature at very, very low pressures, what you find is you miss the liquid phase completely, okay? And so across this phase line, you have sublimation or deposition, depending on which way you're changing the temperature. Make sense? Yeah? Cool. So these can be very useful in figuring out what state a material is going to be in at a specific pressure and temperature. The next one is for carbon dioxide. Okay? Now, carbon dioxide is a fairly interesting material in terms of its phase changes and so forth. So here at 1 atmosphere, okay, the carbon dioxide is solid right up until minus 78.5 degrees Celsius, where it immediately turns into a gas. Okay? So CO2 is one of these things that we can easily get to sublime. Stop. Right. So in this box, I have, as long as I don't freeze my fingers off too much, dry ice. Okay? So this is solid CO2. And what you'll note is that, if I can get it to work, alright. You see it steaming? Some of you? Yep. Alright, so it's turning directly into the gas phase from the solid. There's no liquid phase. And what I can do, that's definitely not working, so we're going to ignore that one. So you can see it better, here's some water. If we pop that in there, okay, you can see it turning directly from the solid to the gas in the beaker. Yep. Cool. All right. I was going to do something else with it as well, but that's not going to work. Right, so liquid CO2 is actually a very rare substance. We don't see it very often. You have to increase the pressure 5 times, okay, and temperature for the triple point here is minus 56.4, which is a temperature that you don't see on the surface of the Earth, okay, unless it's a really, really, really cold day in Antarctica, okay? And so you don't get liquid CO2 very often. You can get liquid CO2 if you take some dry ice and you put it into one of these tubes and let the pressure build up. However, I can't seal the tube properly, so I can't get any. I did try, so you could see some liquid CO2, but it doesn't quite work. If you increase the temperature up to 73 atmospheres, 31.1 degrees Celsius, then you hit this point here. Now this point here is what's called the supercritical point, or critical point to shorten it. Now what happens there is that the CO2 will then turn into what's called a supercritical liquid. Okay? A supercritical liquid is a liquid that looks like a gas, it acts like a gas, but it's incompressible like a liquid. Okay? So it's getting to the point where the intermolecular forces are becoming so chaotic that we really have no idea what phase it's in at all. Okay? It's a liquid, it's a gas, but you can't really tell. Now, supercritical CO2, you wouldn't think would have any uses, but apparently it's very good for decaffeinating coffee. Okay? So most modern decaffeination procedures at the moment use supercritical CO2. So you put coffee into a tank with CO2, pump out all oxygen and everything else, and you increase the pressure right up to 73 atmospheres. Don't ask me what the rest of it does, because I haven't looked at the reaction mechanisms, so I can't tell you. But that's what they do with it. And in the end, what comes out is decaffeinated coffee. Okay? Cool?